Now let us study how to diagonalize a given matrix. Let us try to define and understand diagonalization theorem. An n cross n matrix A is diagonalizable if and only if A has linearly independent eigenvectors. For a given matrix A, we can always compute the eigenvalues. Corresponding to these eigenvalues, we can compute eigenvectors. And if the eigenvectors, whatever we have found out, they are linearly independent, then we can say that the matrix is diagonalizable. For example, let me take a matrix which is A. Say it is a 3 cross 3 matrix. Corresponding to this matrix, we can find out 3 lambda values, eigenvalues. The equation what we use here to find the eigenvalue is determinant of A minus lambda I is equal to 0, which is popularly known as characteristic equation. Once we find the eigenvalues, corresponding to these eigenvalues, we can find the eigenvector. Let me call C as a matrix formed out of these eigenvectors. So the first column corresponds to the eigenvector computed using eigenvalue 1. Second column corresponds to the eigenvector computed using lambda 2. And the third column, it corresponds to lambda 3. And these 3 columns, which are formed by the eigenvectors, they have to be linearly independent. In that case only we can diagonalize a given matrix. Once we know P, we can easily find out P inverse. Knowing P inverse and P, we can compute A, which is given by P D P inverse. Let us try to understand some of the cases or the impact of eigenvalues and eigenvectors on diagonalizability and invertibility. Diagonalizability of A depends on enough eigenvectors. Suppose we have 3 cross 3 matrix, we will be having 3 eigenvalues. Using these 3 eigenvalues, we can compute eigenvectors. And suppose if one of the eigenvalues collapses, then we cannot diagonalize the given matrix A. Invertibility of A depends on non-zero eigenvalues. This is a very important aspect. When we find the eigenvalues, if one of the eigenvalues happens to be 0, then this will not have any impact on the invertibility. Invertibility depends upon non-zero eigenvalues because these eigenvalues usually come in the, when you diagonalize, they come in the they come as a diagonal element. Diagonalization can fail only if there are repeated eigenvalues. Suppose when we compute lambda 1, lambda 2, lambda 3, if lambda 1 is equal to lambda 2, which means that it has a multiplicity of 2, in such cases, whenever we have repeated eigenvalues, diagonalization may fail. Also, we should know that whenever there is a multiplicity eigenvalues, then we should get independent eigenvector corresponding to each of the eigenvalues. We have A minus lambda I. It has a rank of n minus p, where n is the number of columns or a dimension of the matrix, and p is the multiplicity of the eigenvalues. Let us study the procedure involved in diagonalizing a given matrix. Let us consider a matrix A of dimension n cross n. First and foremost thing what you need to do is to find the characteristic polynomial of A. And we have seen from earlier discussion, the characteristic polynomial is given by determinant of A minus lambda I is equal to 0. Solving this characteristic polynomial, we are going to get the eigenvalue. And we need to find the eigenvalues as well as their algebraic multiplicity. To understand the meaning of algebraic multiplicity and the geometric multiplicity, let us take a problem. Consider a matrix A. Let the matrix be 1, 0, minus 1, 1. Let us try to get the characteristic polynomial A minus lambda I is equal to 0. And this is given by 1 minus lambda, 0, minus 1, 1 minus lambda. That will give you 1 minus lambda multiplied by 1 minus lambda is equal to 0. So lambda is equal to 1. Lambda 1 is 1, lambda 2 is 1. We say that lambda is equal to 1. This algebraic multiplicity is equal to 2. Now we try to understand the geometric multiplicity of this matrix. To do that, we have to find the eigenvector. Eigenvector is 1, 0, minus 1, 1. That is A multiplied by x1, x2 should give you lambda multiplied by x1, x2. That will give you x1 is equal to x1 minus x1 plus x2 is equal to x2. In turn, it will give me x1 is equal to 0. So x1 always remains 0. x2 can take any value. So I can write it I can get the eigenvector as x1, x2 is equal to x1 always 0. So x2 0 and x2 is 1 here. So therefore it has got only one eigenvector. So we say that geometric multiplicity is 1. We'll take another example where A is given by 2, 0, 0, 2. So A minus lambda I will give me 2 minus lambda, 0, 0, 2 minus lambda. When I simplify this, I get 2 minus lambda minus 2 minus lambda is equal to 0, which will give me lambda is equal to 2, with arithmetic multiplicity, algebraic multiplicity is equal to 2. Now we try to find the eigenvector for eigenvectors are here 2, 0, 0, 2 multiplied by x1, x2. That will give me 2 into 2 into x1, x2. So here it gives the equation 2x1 equal to 2x1. So x1 equal to x1. Here 2x2 is equal to 2x2. That gives you x2 equal to x2. So therefore I can write x1, x2 is equal to x1. It is 1, 0 from the first equation. Second equation I get this as 0, 1. So I have two eigenvectors corresponding to the eigenvalue. So therefore your geometric multiplicity in this case it is 2. Knowing this algebraic multiplicity and geometric multiplicity, we discuss the third point in diagonalizing a matrix. We need to compute the eigenvalues using the characteristic equation given by A minus lambda I determinant is equal to 0. And we need to find for each eigenvalue its algebraic and geometric multiplicity. And if geometric multiplicity for each eigenvalue is less than that of the algebraic multiplicity, then it is matrix is not diagonalizable. Therefore, we will not proceed to the next step. Otherwise, we can go to the next step and we can find the eigenvectors corresponding to each of these eigen values. And the eigenvectors computed, let's see, v1, v2 up to vn, we have to check for their linear independency. If they are linearly independent, then we can compute the matrix P, and the matrix P is given by the columns v1, v2 up to vn. Some books refer it as equal to, this is called as S. Now, once we know P, we can always find out inverse P. So, knowing P inverse P, we can find the diagonalized matrix. We can diagonalize the given matrix using the formula B is equal to P inverse A P, or it is X inverse A S. We try to understand the principle of diagonalization of matrix with an example. I have taken an example of a matrix which is a 3 cross 3 matrix. Let me call it as A, defined in the element 4 minus 3 minus 2 in the first row, 3 minus 2 minus 2 in the second row, minus 1, 1, 2 in the third. Step number 1, we need to find the characteristic polynomial. We know that characteristic polynomial can be found by taking the determinant of A minus lambda I and equating it to 0. And A minus lambda I will give me, this is A matrix, minus, it's a 3 cross 3 matrix, lambda into I will give me lambda 0, 0, 0 lambda 0, 0, 0 lambda. When I take the determinant of this and I have to equate it to 0, I am going to get the characteristic polynomial. That is 4 minus lambda minus 3 minus 2. 3 minus 2 minus lambda minus 2 minus 1, 1, 2 minus lambda will equate it to 0. We get the polynomial as, when we simplify this, we get this as 4 minus lambda multiplied by minus 2 minus lambda, 2 minus lambda plus 3, and this is equal to plus 3. That will give you 3, 2 minus lambda, it is minus 3. Then we have minus 3, it is 3 minus it is 2 plus lambda. That should be equated to 0. When I simplify this equation, I am going to get the characteristic polynomial lambda cube minus 4 lambda square plus 5 lambda minus 2 equal to 0. Second step is to need to find the eigenvalues from this characteristic polynomial. We get 3 eigenvalues, 1, 1 and 2. And here lambda is equal to 1 has a algebraic multiplicity of 2. Lambda is equal to 2 has an algebraic multiplicity of 1. Let me try to find out the eigenbases. For lambda is equal to 1, with lambda is equal to 1, I have matrix A multiplied by 3 variables x1, x2, x3 is equal to lambda is equal to 1 multiplied by x1, x2, x3. When I simplify this, I get the equation 4x1 minus 3x2 minus 2x3 is equal to x1, which will give me 3x1 minus 3x2 minus 3x3 is equal to 0. In other words, I can write that x1 is equal to x2 plus x3. Let me take the second row of this matrix A. It is 3 into x1 minus 2x2 minus 3x3 is equal to x2. When I simplify this, once again I get this as 3x1 minus 3x2 minus 3x3 equal to 0. So further simplification will give me x1 is equal to x2 plus x3. We take the third one, we have minus x1 plus x2 plus 2x3 is equal to x3. When I simplify this, I get minus x1 plus x2 plus x3. Further simplification will give me x1 equal to x2 and plus x3. Therefore, I have the three variables x1, x2, x3 is equal to, this is x2. x2 multiplied by 1, 1, 0, because x1 has x2 here, so that's why this 1, and x2 itself is 1 here, plus x3, it is here you have x3 equal to 1, so 1, 0, x2 is 0, and x3 is equal to 1. So we have here the two eigen basis for two eigen space, or I can say two eigenvectors. They are defined as 1, 1, 0, 1, 0, 1. And you can see that they are linearly independent. Suppose if I multiply the first column, first eigenvector by 1, I cannot get the second eigenvector. They are linearly independent. And also we are seeing here that the geometric multiplicity is also 2. So for algebraic multiplicity of 2, so we can proceed to the next step. We take the next eigenvalue, lambda is equal to 2, and its algebraic multiplicity is only 1. We have matrix A multiplied by the three variables x1, x2, x3, which is lambda is equal to 2 multiplied by x1, x2, x3. They are being equated. When I simplify this, I get 4 into x1 minus 3x2 minus 3x3 is equal to 2 into x1. Further simplification will give me 2x1 minus 3x2 minus 3x3 is equal to 0. Similarly, I will take the second row, I multiply with these three variables. I get this as 3x1 minus 2x2 minus 3x3 is equal to 2x2, which will give me 3x1 minus 4x2 minus 3x3 is equal to 0. The last one will give me minus x1 plus x2 plus 2x3 is equal to 2 times x3. That will give me minus x1 plus x2 is equal to 0. That gives me x1 is equal to x2. Once I know x1 is equal to x2, I can get 3x2 is equal to 3x1 minus 4x2. That will give me minus of x2. So therefore, x3 is equal to minus 1 by 3 x2. So you can substitute in the very first equation here, and here we have got from here x1 equal to x2. So we can get here, we can verify this here. It is 2x2 and it is minus 3x2 and minus 3, it is minus 1 by 3x2. So it becomes plus. So here we have got minus x2 and here we have got plus x2 equal to 0. This is what we have done as a verification. Now I can write the variables x1, x2, x3 in terms of x2. x1 is equal to x2, where x2 itself is 1 and x3 is given by minus 1 by 3. So therefore, the basis for the eigenspace or the eigenvector is given by 1, 1, minus 3. It can be further written as this basis is given by 1, 1, minus 1 by 3, and we can simplify this by multiplying it by 3. Then this is going to be here it is, we are multiplying it by 3. So therefore, we get this as 3, 3 minus 1. This is the eigenvector. Here you can see that geometric multiplicity is 1, algebraic multiplicity is 1. So we can move to the next step. Fourth step is to find the linear independency of these eigenvectors. So we have three eigenvectors defined as v1 is equal to 1, 1, 0, v2 is equal to 1, 0, 1, v3 is equal to 3, 3 minus 1. Now let me check the linear independence between these two vectors. If I multiply this by 1, I am going to get this as 1, 1, 0, but I have 1, 0, 1. So definitely these, by multiplying v1 with any scalar quantity, I am not going to get v2. So they are linearly independent. Let me check between v1 and v3. Multiply v1 with 3. I am going to get this as 3, 3, 0, but I have minus 1 here. So we can say that v1 and v3 are linearly independent. Another method is to find the determinant of these vectors, and we have already called this as P, and this is equal to 1, 1, 0, 1, 0, 1, 3, 3 minus 1. So this should be invertible matrix. That means when I take the determinant of this, this should not be equal to 0. Then only I can take a inverse of this matrix. So I can do it by taking the determinant. This is 1 into minus 3 minus 1, it is plus 1, minus 3, it is 1. This and this will get cancelled out. So here I have, this is minus, so it is equal to 1. So definitely this is not equal to 0. So P is invertible matrix, and we can say that these three vectors v1, v2, v3 are linearly independent. And as I said earlier, some people call this matrix as S. Instead of P, they denote it by S. You can define the diagonal matrix D directly from the eigenvalue. D is equal to, these three are the eigenvalues, that is 1, 1 and 2 as the diagonal elements of the matrix. So here you can see that lambda is equal to 1. It refers to the column vector 1, 1, 0. And when lambda is equal to 1, here in the second column and second row, it refers to the column eigenvector v2, 1, 0, 1. And then we have the third one, that is lambda is equal to 2. It's in the third row and the third column. It refers to the eigenvector 3, 3 minus 1. The seventh step is to compute the diagonal matrix D using the equation P inverse AP. P is given as 1, 1, 0, 1, 0, 1, 3, 3 minus 1. When we take the inverse of P, we get this as minus 3, 4, 3. 1 minus 1 0, 1 minus 1 minus 1. So P inverse AC, this is P inverse, this completes A, and this is C. So when we multiply all these three matrices, we are going to get 1 0 0, 0 1 0, 0 0 2, that we have defined earlier with eigenvalue, that is equal to B. Thank you. In the next video, we try to understand the special matrices.